Hi everyone, welcome again to another edition of the Focus on Geothermal webinar series. This is an initiative of a partnership between ThinkGeo Energy and our partner Enerchange. I am Carlo Cariaga of ThinkGeo Energy, and I have the pleasure of introducing to you our speaker for today, Pieter Bruijnen from EBN in the Netherlands. And he will be speaking about the topic of well testing procedure for geothermal wells that implements downhole shut-in instead of a surface shut-in. So based on the project or the study, this method provides a more accurate measurement of the reservoir response. Peter is currently a reservoir and production engineer at EBN in the Netherlands. At EBN, he is involved in the development of the geothermal industry and in underground hydrogen storage. He had previously worked as a petroleum engineer at Taka Energy and as a reservoir engineer for SGS. His interests include reservoir characterization, reservoir and well performance, production optimization, and systems integration. Peter holds a Master of Science degree in geology from the Utrecht University and another Master's of Science in Petroleum Engineering from the Heriot-Watt University in Edinburgh. For the audience, you are free to send in your questions. There should be a questions tab in your webinar panel, and then just type in your questions at any point, and then we'll get to them after the presentation. So, Peter, thank you for being here, and the floor is yours.
Thank you, Carlo. Thank you for this nice introduction. Welcome, everybody. It's a pleasure presenting to you today. I'm happy to show something interesting to you. During the last few years, I've done some research on geothermal well testing, low enthalpy reservoirs, and I found it very interesting. And in fact, I think it's so interesting and relevant for the sector, and that I would like to share some of this research with you today. Yeah, well testing is quite a niche, and I would like everyone in this webinar to understand what I'm saying. Therefore, I'll start with a little bit of background on well testing, because if you have not heard of two specific concepts yet, then you might not be able to follow my presentation. So the first concept that I want to tell to you is the concept of derivative. Derivative is just a method of plotting data. And the second concept is the concept of wellbore storage. And wellbore storage or wellbore dynamics or wellbore physics is just all the physics that are present in the wellbore at the moment of shutting in the well, so during the well testing. And wellbore storage effects have a big impact on the derivative, and therefore it's important that I explain both to you. And I'll show you what the impact is of wellbore storage using some field cases of geothermal wells. And then I'll continue to show some numerical simulations, and those simulations explain what happens exactly in the wellbore during a buildup, and also how wellbore storage effects can or maybe even will lead to an incorrect interpretation of the well test. So it's very important that we try to avoid wellbore storage, and there is luckily a very easy way to avoid that, and that's a downhole shut-in. Let me get the point, a downhole shut-in. And then finally, I'll show you one more field case of a well we recently drilled. It's the Oranje Ocht 1 well, where we installed a downhole shut-in device. And by showing you the well test of that well, I can show you the effectiveness of such a downhole shut-in. All right, some background. This is how a typical well test looks like or could look like. It's a well Hayes 1. The Nederweert sandstone formation is a Triassic sandstone in the Netherlands. This graph starts at the 15th of December last year and ends at the 17th of December, so it's a time period of 2 days. Well tests, usually you start flowing the well, then you stop the well, you shut in the well, then there's another flow period, then we shut in for a longer period, typically 24 hours. So flow period, shut in, and another flow period and shut in. During these flow periods and shut-in periods, we install a downhole pressure gauge, and that pressure gauge records what is happening inside the wellbore during the production and the shut-in periods. And that is shown here. If we stop the well, then the pressure suddenly builds up, and when we open the well, we start producing again, suddenly the pressure drops and it flattens out to a certain value. Then we shut in the well again, and the pressure starts building up rapidly and gradually flattens out. These buildups, you see 4 of them. These buildups are typically what reservoir engineers are interested in, because the shape of this buildup curve reveals the reservoir properties of interest. The shape of this curve is dictated by the permeability, by the skin, by the presence of faults, by other geological properties. But the question is, how do you draw conclusions regarding the reservoir based on the shape? And reservoir engineers have found a trick to do that. And that is the derivative. And the first graph is another buildup. So the pressure rapidly builds up and then flattens out. And the trick is that reservoir engineers do not plot this buildup anymore, but they plot, in fact, the pressure difference between the second data point and the first one, and the third one and the first one, the fourth one and the first one, etc. That is shown here. So here we plot the pressure difference, not the pressure anymore, but the pressure difference. And not on a linear scale, but on a logarithmic scale. And so the pressure difference is plotted on a logarithmic scale, and the time is also plotted on a logarithmic scale. Then the last step is that we take the derivative of this curve. So the derivative of this curve that looks like this red curve. And that's the concept of a derivative. So just a different method of plotting the build-up data. And why do we do it? Because now suddenly some details will be visible that are not visible in this curve. So it's just a method of exaggerating tiny details that would be otherwise invisible. I'll show you that on this slide. Let's imagine you have an infinite reservoir, infinitely large, and it's heterogeneous. Then the derivative looks like this. It very rapidly flattens out to a certain horizontal line. And the level of this horizontal line, that is a measure for the transmissivity, or the KH. If that line would be somewhere else, if that line would be, for example, here, if the horizontal line would be here, then the KH is higher. If that horizontal line would be, for example, here, then the KH would be lower. The other very important parameter that we want to draw conclusions of based on the well test is the skin value. And the skin is the difference between this blue line and that stabilized red line. So the length of this arrow is a measure for the value of the skin. The larger the arrow, the higher the skin is. Now, what are the details that I was talking about? Let's imagine the middle picture, you have a fault in your reservoir. Then the derivative will look like this. It's still flattening out here. So this is the KH, or the transmissivity. But at some point here, the derivative starts deviating from the horizontal line. And the onset of this deviation, that is a distance of the fault to the well. And after that, the derivative starts to become horizontal again, and it's flattening out. So the KH is this first stabilization line and not the second stabilization line. And what's the skin value in this specific case? It's still the distance between the blue line and the first stabilization, not between the blue one and the second stabilization. And just another example, imagine you have a naturally fractured reservoir, then the derivative would look like this. It's flattening out here. Then there is a valley, and the width and the depth of the valley, that's indicative for the fractured network. So by analyzing these derivatives, you can draw very firm conclusions regarding the reservoir properties. Okay, then the other concept, that's the concept of wellbore storage or wellbore physics. And that's, as I said, all the physics that are happening inside the well at the moment of shutting in the well. So imagine you have a well, you are producing the well, then you shut in the well, and at that very moment, I took this picture. So here on the left side is the sorry. There on the left side is a well that was on production using gas lift. Then we shut in the well, and at that moment, this is what a well could look like. We injected a gas, usually nitrogen, using the core tubing. And when you stop the injection of gas and shut in the well here at surface, all these gas bubbles are still migrating upwards. That might take up to 2 hours before the gas bubbles have reached the surface. While they are migrating upwards, the gas bubbles expand because the pressure is getting lower, and they accumulate here on top of the well. So a cushion of gas is being formed, and the cushion of gas, as it's growing, it pushes the water downwards into the reservoir. Because if the gas goes up, something else must go down. So the water goes down because it's heavier than the gas. The right picture is a ESP lifted well. So again, we put the well on production with the ESP, then we shut in the well, and that is the moment when I took this picture. The ESP has created a fluid column inside the tubing. It's an artificial fluid column caused by the motor inside the ESP and the pump. And the weight of this fluid column is very heavy because it's a very dense water. At the same time, the ESP has created a under pressure in the reservoir or the drawdown. So that means when you remove abruptly this artificial pressure increase, that very heavy fluid column inside the tubing will fall down into the reservoir. So it will temporarily be an injection well. At the same time, if the water level or if the water falls down, a gas will form here. The water inside the tubing will vaporize. So a sort of a vacuum will form. And that will have a big impact on the pressure gauge located here at the bottom of the well. The problem is that these pressure gauges, you want to measure the pressure signal from the reservoir, but what the pressure gauge also measures is, in the case of an ESP, this vacuum here that's being formed, or the fluid level in the analyst that's going up, or the communication between the tubing and the analyst. And in the case of gas lift, this pressure gauge does not only measure the pressure response from the reservoir, but it also measures the buoyancy effects or the cooling effects, the heat exchange between the gas and the overburden. And the same applies for this well here. So what the gauge measures is the sum of all the pressure responses from the reservoir. And that's always the only objective of well testing. But the gauge also measures a whole range of side effects of undesirable noise. And that's called wellbore physics or wellbore storage. And by default, everybody hates them because they overprint or blur this reservoir signal. And that's a big problem in well testing. So what does the literature say, or software? Well, they say the same. Wellbore storage effects are highly undesirable. They overprint the reservoir signal. And wellbore storage effects, they can be dealt with mathematically. If the wellbore storage effects are short, say seconds or minutes, and if the wellbore storage effects are not extreme, meaning that the impact they have is less than the impact of the pressure response from the reservoir. So what do we mean with wellbore storage effects are short? Well, let's go back 2 slides. You see this little hump here? This little hump, this is a wellbore storage effect. This is caused by the wellbore physics inside the wellbore. And you see that the wellbore storage effects, they stop about here at 0.01 hour, and they gradually move into a different flow regime indicating the transmissivity. And so as long as the wellbore storage effects last for 36 seconds, then you have plenty of room in this graph to interpret your KH. But what if the wellbore storage effects would be longer than, for example, like this? This is what it could look like. Or in a more extreme case, the wellbore storage effects would look something like this. Well, then you can still interpret the KH, isn't it? But now, what if you have in the middle picture, a fault in your reservoir, and you have wellbore storage effects? Well, in the case that I draw here, the wellbore storage effects are short, 36 seconds, maybe 1 minute, so you can still interpret your KH. But if the wellbore storage effects last longer, something like this, then you don't see anymore what your transmissivity is. And then you don't see anymore where the onset of the fault is. And the same applies if you have a naturally fractured reservoir. If the wellbore storage effects look something like this, you cannot see anymore what the properties of the natural fractured network are. And for that reason, the wellbore storage effects are very, very bad. Now there's this company, S&P Global, previously known as faculty. They published the golden rules of well testing. And one of the rules, rule number 8, is if it happens suddenly in your derivative, it's not a reservoir effect, but a wellbore effect. And I really like that rule because shown here are some derivatives of geothermal wells in the Netherlands. They are all publicly available. The left picture are the derivatives of a buildup following an ESP assisted production period. On the right are the derivatives of buildups following gas lifted production periods. And just by looking at these data, you can already conclude that we are probably looking at wellbore storage effects. And why is that? Well, because of this rule, if it happens suddenly, it's not a reservoir effect, but a wellbore effect. For example, this little kink here in this derivative. This is very abrupt change in direction of the derivative. So according to that company who published the golden rules, this is most likely a wellbore storage effect. And the same applies for example here, very sharp and sudden kink. But there's something else what makes me think that we are looking at wellbore storage effects, and that's indicated with these arrows. For example, this orange arrow or this orange graph, you see here this nice curve, it's going up, and then very suddenly it is going down into a massive valley. In fact, the valley is so deep that it falls off the scale. And then after another hour, an additional hour, it recovers and then goes further. Or this blue curve, it's going down, going down, going down, going down. It suddenly disappears at 0.8 hours, and it does not recover until 2-3 hours to reappear again here. This also looks like a wellbore storage effect because I've never seen this in any oil and gas well, and it's not typical according to the textbook examples. If you look up how a typical oil and gas well should look like. And moreover, it looks like as if many of these derivatives are not stabilizing. For example, this green curve, it's going down, going down, going down, going down. There's no stabilization period. And the same for this black line, it's going down, going down, going down. All of them do not seem to stabilize. There's one well, an anonymous well, well A, that I want to dive into a bit deeper. It's a geothermal well that we drilled a couple of years ago in the Netherlands. And shown here are 3 different pictures of one and the same well test. Let's start with the picture on the right here. I plotted here vertically the wellhead pressure during the buildup and the temperature of the wellhead during the buildup. And so the well was on production for a couple of hours with an ESP. Then we shut in the well and measured the buildup pressure and the buildup temperature. And those pressures at the wellhead are plotted here. So A is the moment of shutting in the well, and B, C, D, E, F. F is the wellhead pressure and the temperature after 100 hours of a buildup. And you see that at the moment of shutting in the well, the pressure very abruptly drops to B. So it starts at a pressure 4 bar, wellhead pressure 4 bar. That used to be the operating pressure when we produce the well. Then it drops, it keeps dropping, it drops to a value of 0.3 bar. Wow, that is very vacuum. And simultaneously, as you see, the temperature drops because of the heat exchange of the wellhead between the wellhead and the atmosphere. So the pressure is dropping and temperature is dropping to very low values. This picture here on the left is the same wellhead, or the same well. Plotted here is the gas-water interface inside the tubing and inside the annulus. And the same letters here, A, B, C, D, E, and F. And you see that at the moment of shutting in the well, A, there is no gas-water interface in the well because it's a geothermal well without any gas. But very soon after shutting in the well, there is a gas-water interface. And the interface drops to a level of 500 meters. It means there is more than 500 meters of gas in the well, water vapor. Why is it water vapor and not gas? Well, if you look at this picture here to the right, I also plotted here a vaporization curve. And the vaporization curve, or a phase diagram, shows where a gas turns into a liquid or the other way around. And so if you boil water, for example, at 100 degrees Celsius, then it starts boiling at a pressure of 1 bar. Well, this curve is not exactly at 1 bar because it's not water, but it's a geothermal brine. So a lot of dissolved salts and dissolved gases are inside the brine. So the shape of this curve is, it looks like water, but it's in fact the shape of a geothermal brine. And many of these data points lie exactly on this vaporization curve. So that means between B and C, the water is vaporizing. So it's boiling. So between B and C, the water is boiling, and it coincides between B and C with this fluid level and tubing going down massively and then recovering to C. And between C and D, the data points are not on this line anymore. It means that the system is condensating, so condense is being formed. And between C and D, the well is recovering to E and F, but even after 100 hours, it's still not stable yet. The fluid level is still going up. Now, how does the derivative look like? Well, we start here at A, then B. From A to B, it's sort of normal, but then from B onwards, when the water level and tubing is going down, that coincides with this massive valley here. And it's not until C where it's almost normal, but it's back to the previous value again. That's here. And between C, D, E, and F, it's not stabilizing yet. And I think because fluid level is still not stable yet. So we're just looking at these data. You can already conclude that we're not looking at any reservoir properties. We're just looking at vaporization, condensation, fluid levels that are going down and up again. And that determines the shape of this derivative. Okay, then I did some numerical simulations in Eclipse 100. That's a thermal simulator. And the goal of this simulator was to assess the impact of wellbore storage effects on the derivative. And I built a very simple, straightforward reservoir model shown here. But in addition to that, I did not use an analytical wellbore model. That's what reservoir engineers usually do. But I used a numerical model instead, where I divided the wellbore into 250 segments. I discretized the wellbore into 250 segments. These segments or cells are connected to the grid. And by doing so, I could assign certain wellbore physics to the cells, including the enthalpy, the friction, heat transfer, etc. And thus I was able to model wellbore storage effects. And another advantage of modeling wells like this is that you can shut off certain segments. For example, this one here, the blue one. And by shutting in this one, I can mimic a downhole shut-in. Or alternatively, I could close this segment, and by doing so, I could mimic a surface shut-in. So I made 3 models. The first one was a model where I produced a well with an ESP somewhere here in the middle and used a surface shut-in. And by doing so, a downhole pressure gauge here measures the reservoir signal, but also the wellbore physics. And the second model was a buildup preceded by gas lift, followed by a surface shut-in. And as a reference case, I made a buildup with a downhole shut-in. And the results look like this. The left pictures are the model with the ESP, and the right pictures are the models with gas lift. Vertically is the well depth in meters, so this well was 2 kilometers deep. And horizontally is the time of the buildup, shown here from 0 to 100 hours, so pretty long buildup. And in case the buildup shown here was preceded by lift with an ESP, then you see that at the moment of the buildup, the entire well was blue, meaning that the gas holdup was 0 or the water holdup was 1. So the entire wellbore is filled with water. But at some point during the buildup, at this moment, so very shortly after the buildup, the gas starts to form here because the gas buildup suddenly becomes 1 here, which is the water vapor as we saw before. Now, if we look in the second picture, if we look at the direction the water is flowing at inside the tubing, that's shown here. Red means that the water in the well is flowing down. Green means the water is flowing upwards, and yellow means stationary. So if you lift a well with an ESP, at the moment of shutting in the well, all the water is falling down, and it takes up to this moment, which is 2-3 hours before the water level becomes stationary. So that means gas is being formed, the water vapor, water is falling down, and if you make a buildup of the downhole pressure gauge and plot that on a logarithmic scale and take the derivative of that, then the graph looks like this. So this is the derivative of the buildup of an ESP lifted well. You see this major valley here that we also saw on these field cases. Here's the major valley. Where the arrow is a valley, and you see the same valley here, right? As a comparison, I also made a model where I shut in the well here instead of here. So by shutting in the well here, I remove all the wellbore storage effects. Then the derivative looks like a very normal, straight, smooth horizontal line. And you clearly see that it takes up to 4 hours maybe before the two lines converge. So that means that on the blue derivative, everything before 4 hours are wellbore storage effects. Everything after 4 hours is representative for the reservoir. Then just for the sake of time, I'll just skip these right pictures, but it's the same, but then for gas. One more numerical simulation. I wanted to investigate to what extent Weber storage effects can lead to wrong conclusions. And I made two more models. The first one, well, both models are actually identical, Model 1 and Model 2. The reservoir has a transmissivity of 15 Darcy meter in both cases, a skin of 10 in both cases, and I inserted a sealing fault here at 200 meters from the well. Same here, sealing fault at 200 meters from the well. The only difference between Model 1 and Model 2 is that in Model 1 I shut in the well downhole, therefore removing all Weber storage effects. And in Model 2 I shut in the well at surface, therefore including all the Weber storage effects. And from the simulations, I exported the downhole pressures of a downhole pressure gauge that is installed here. So below the downhole shut-in valve, and here, yeah, same depth, of course. The results are shown on this slide. So Model 1 is with a downhole shut-in. Plotted here, these red dots is the same derivative as you've seen before. Very small and short wellbore storage period. Why is there still some wellbore storage? Well, because there is still one cell here that contains fluids, so also a little bit of wellbore storage. But very soon, you see this horizontal line. You see the onset of the fault at 200 meters, and then it stabilizes to a second stabilization period. Then the next step I did is exporting these red dots to Kappa. Kappa is analytical software that is frequently used to interpret well tests. And I let Kappa decide what the transmissivity and the skin is of this synthetic data set. So I treated this synthetic data set generated in Eclipse as if it were a real data set obtained from a real well in a real reservoir. And Kappa made this model, the black line. Kappa made a model that almost perfectly matches the synthetic data, except maybe a little bit for here's a slight off match, but for the rest, the model was very well able to calculate what the KH is and to calculate the skin. Because the answer that Kappa was giving me is that because of this perfect match, Kappa said the KH is 15 Darcy meter. Well, that's correct, because in Eclipse it was 15 Darcy meter indeed. Kappa said the skin is 10. That's correct, because I inserted the skin of 10 in Eclipse. And this onset here is correctly modeled by Kappa. Kappa thinks that the fall distance is 200 meters. That's correct, because I modeled a fall distance of 200 meters. So the conclusion is that the analytical software can very much reproduce the true values of the reservoir and the skin. So that's good news. But then let's go to Model 2. Remember where I used a surface shut-in. I did the same methodology. I created a synthetic data set in Eclipse. That's the blue line and the red dots. You see here this hump, then going into this massive deep valley here, recovering after a couple of hours, and then you see the transmissivity. I exported this data set to Kappa again, and I used Kappa to calculate or to back calculate what the KH and the skin and the distance to the fault was. The model that Kappa made is reasonable. It looks like a rather neat match, but the outcome of Kappa is different, because the first stabilization period that's clearly shown here is not visible here anymore. That means that this second stabilization period looks like as if it was the first one. But it's not. This is the second stabilization period. Well, it appears to be the first one. So Kappa now thinks that this is the first stabilization period, and therefore the KH is 7.5 Darcymeter. So that's wrong. The software thinks it's 7.5, while it should be 15. And the same applies for the skin. The skin is the vertical distance between the blue line and the first stabilization period. But in case of model 2, this looks like the first stabilization period, and therefore this arrow is shorter. And the analytical software thinks that the skin is 0, which is not, it's 10. And because you don't see a first and second stabilization period, you cannot determine where the onset of the fault is. In fact, I don't see a fault in these data. And the same holds for Kappa. Kappa didn't observe a fault either. So by not including a downhole shut-in, this is what you think are the reservoir properties, while they are this. So the KH is off by a factor 2, the skin is massively off, and you cannot observe a fault anymore. So that's the conclusion. If you do not install a downhole shut-in, the results of the well tests might be completely off. Very wrong. Now, is there a solution? Yes, luckily there is. And the solution is pretty simple. And that's a downhole shut-in device or a downhole shut-in tool. That's just nothing more than a valve installed here, preferably as close to the perforations as possible, but always above the gauge, of course. By installing such a downhole shut-in device, all the wellbore storage effects are completely excluded from the measurements done by the gauge. And it's not new with downhole shut-in device. It's available since the 50s. The pressure and temperature ranges are large. You can deploy them by E-line, slickline, cold tubing, or DST, whenever. So it does not have to be expensive. It can be done as cheaply as any other slickline operation. And yeah, one more slide. We drilled as well Oranje 1 last year, and we did 2 well tests. One well test with a downhole shut-in device and a well test without a downhole shut-in device. And the difference is shown here. The well test with a downhole shut-in device, so excluding the wellbore storage effects, looks very smooth. It's very easy to draw conclusions regarding where it's becoming horizontal. So very straightforward line. However, with a surface shut-in, so without the downhole shut-in device, it's a big mess. It's a complete chaos and hardly possible to draw any conclusions with such a buildup. Yeah, so there's one conclusion, one recommendation. If you do a geothermal well test, always use a downhole shut-in device. Otherwise, you will most likely end up with incorrect conclusions. Okay, well, that's it. Thank you very much for your patience. I can imagine there are some questions, so feel free to ask them.
Okay, thank you, Peter. That was a very eye-opening study, I would say, and it's also, I would say, it's also something that challenges a lot of the practices that the geothermal industry has done for perhaps a few decades. And so, what do you think how do you think will, say, industry players respond to this kind of proposals such that does it mean that any of their old databases of reservoir response are not as accurate or as useful anymore?
Might very well be, yeah. If the reservoir is homogeneous and there are no faults or naturally fractured reservoirs, then the conclusions might be correct if you have not applied the downhole shut-in. But if there is something within 4 hours between the moment of shutting in and the 4 hours of the pressure wave prograding into the reservoir, that means a radius of a couple of hundreds of meters, anything in between that area might be invisible to the well test. So if there is a geological change within 400, 500, 600 meters maybe or longer, then you will not be able to see it. If it's homogeneous within that range, which is highly unlikely, I think, then the well test interpretation might be correct.
Well, okay then. Well, I've looked at some reservoir response plots in the past, and I've always kind of thought that wellbore storage effects are just natural, and there's this certain ambiguity as well in interpreting them. But it did not realize that there's this danger of them perhaps overprinting or hiding certain indicators of reservoir response, and so I think that's definitely where the value is. Okay, so we have a couple of questions from the audience. Also, for anyone listening in, just feel free to send in your questions as well. I'll go through these questions. How about injection tests? Is there any sort of version of this procedure that applies to testing with injection?
Yes, it would be best to include a downhole cylinder device as well during injection tests. The problem might not be as severe because during an injection test, you also create a drawdown, but it's an inverse drawdown, and you create a pressure increase in the near wellbore area. So when you stop the injection, that very dense water column falls into the reservoir, but because there is no underpressure in the reservoir, it might take much longer for the well to develop a vacuum. And once you have created that vacuum, that's the moment when the wellbore storage effects become dominant. So as long as your wellhead pressure remains above approximately atmospheric pressure, then a well test, an injection test could be fine. But just to be safe, I recommend just to install a downhole shut-in device.
Okay then. So, I mean, ensuring better data is one thing, but also there's the more practical side of implementing such tests. So, what can you make a comment on how much more expensive or how much more time it would take to implement a downhole shut-in versus a surface shut-in?
Yeah, that depends very much on how you want to deploy a downhole shut-in device. If you do an E-line or slick line or coiled tubing, that's then the costs are minimal. I would say an additional 50,000 euro maybe, but that depends, of course, on your contract, on your supplier. You can do more fancy stuff with a DST, for example. Then you can sample as well, but then the costs might be much larger. So it's up to the operator on the budget and to the service companies what they can provide. But most important, it doesn't have to be expensive. If you install it as part of the normal data gathering suite, then it's definitely worth doing it. And there are many options. It's available for 75 years now. So I'm sure there will be a solution for your specific well.
Okay then. And to clarify, this study applies to wells that require artificial lift. It does not. Does it also apply to wells that can provide artificial flow rather?
Are there any geothermal wells that do not require artificial lift? If that is the case, because, for example, the reservoir pressure is extremely high, or the weight of the fluid column is very low, in that case, the wellbore storage effects will not be so extreme as the cases I just showed you, but then they fall in the category of oil and gas, I would say, because oil and gas wells also flow, well, gas flows naturally, oil wells flow either naturally or artificially, and wellbore storage effects are usually much smaller in oil and gas wells than in the case of the very dense water that we have in low enthalpy geothermal wells. So I'm not sure. I think that there will be wellbore storage effects because you can hardly prevent any of them, but it might not be as severe as for conventional geothermal wells, I would say, where you have to use some form of artificial lift. But
Yeah,
with the
there's an interesting comment here that there is such a thing in the Upper Rhine-Graben, but then there's also an effect of CO2 degassing, which I imagine would also create a wellbore storage effect, right?
yeah. As long as you have a gas, especially when the pressure of the gas is very low, then you have a very high compressibility of the gas, and the compressibility forms part of the wellbore storage effects. And another reason why the wellbore storage effects can be very extreme in geothermal wells is because the size of the wells is so massive. Quite often the geothermal wells, at least in the Netherlands, they do not have a packer, and therefore the volume that is exposed to wellbore storage effects is the entire volume of the tubing plus the annulus. And it can easily add up to 200 cubic meters of volume. And the wellbore storage effect is the combined effect of wellbore volume and compressibility of the fluids or the gases. So if you have a large well with gases having a low pressure and therefore a high compressibility, that's when the most wellbore storage effects will be most extreme. But as far as I'm concerned, but I might be wrong, artificial lift is still required in the Upper Rhine-Graben. It's not with an ESP, but with a line shaft pump, but it's still artificial lift.
Is the effect the same whether you get an ESP or a line shaft pump?
And I think so, because it's still a method of artificially creating a head. As long as you create something artificially, and when you stop the pump, then the head or the water column falls back into the reservoir. Unless you found a method to prevent that. Maybe you have a bypass valve somewhere or another way to prevent that the water's falling back. But if the water falls back into the reservoir, then you will get severe wellbore storage effects.
Yeah, I think that makes sense too. Okay, then something more practical again. Where would you position a downhole shut-in mechanism? Would you put it like immediately above a pressure gauge or just right below the artificial lift mechanism?
The deeper the better. Because in this case, for example, all the volume below the shut-in device still contributes to wellbore storage effects. So you have to minimize this volume. And you have to minimize, but that's not up to you, you have to minimize the compressibility of the fluids inside that volume. So you can install the valve not here, but just below the ESP. Then the volume below the valve will be much larger, and therefore the wellbore storage effects will be more extreme. So the deeper, the better, always. But most important, try to minimize the wellbore volume by installing the device as deep as possible.
Okay then. Earlier you showed side-by-side comparisons of simulations run on a well that was tested with both either surface shut-in or downhole shut-in. So from these learnings, would it still be possible to say retroactively process old data that did not have downhole shut-in and make them kind of a bit more accurate based on your findings?
You cannot do that using the conventional software that is used, and that is the analytical software like Kappa or Vacuity, because those software companies they have not included any mathematical models to deal with such massive wellbore storage effects, because there are no mathematical solution to that. The only solution would be theoretically to use numerical simulations, just the way I did, because I was able to model wellbore storage effects using numerical models, but the degrees of freedom that you have in these numerical models will be massive. And normally, the reservoir by itself contains already too many variables. If you include the wellbore, including the casings and the cement and the overburden and all the thermal properties of everything between the wellhead and the reservoir, then it's then you will always get a match between the model and the data because there are too many degrees of freedom. So theoretically, yes, you can use a numerical model to match this, but in practice, it will be not possible, I'm afraid. Or you might achieve a match while the results are still not correct, because you always get a match if you tune a certain parameter, but you might have selected the wrong parameter to tune. And so I would recommend not trying it and install a downhole device instead. Might also be cheaper.
Okay, another follow-up comment on what we talked about the wells in the Upper Rhine Graben having natural gas lift. Someone from the audience also pointed out that this is also the case in the Pannonian Basin in Croatia. But then these also have natural flow, but also have a lot of natural gas lift, and so wellbore storage effects are to be expected as well.
Yeah, it could very well be. I'm not aware of those wells. I recommend have a look at them, see if you have any strange phenomena like these arrows or these circles that are not in the textbooks. Then if they're not in there, or when the derivatives are not stabilizing, then there might be a good indication that those wells exhibit wellbore storage effects as well. Yeah.
There is a more general comment here. What is the proportion of is there a ballpark value of the proportion of undesirable noise from all the other pressures compared to the actual pressure from the reservoir response?
No. The lower the better, and the shorter the better. What I tried to explain, where is it? Yeah, here. If the wellbore storage effects last less than a minute or so, then the radius of investigation will be a few meters into the reservoir. That means in the worst case, the first few meters into the reservoir are invisible in the well test. But since this is a logarithmic scale, now one log cycle further is maybe 100 meters into the reservoir instead of a few meters. So the shorter the wellbore storage period is, the better. But is there a rule of thumb? No, I don't think so, unfortunately.
Okay, then. So it really is a matter of seeing how long the wellbore storage effect lasts. What would you recommend operators do a surface shut-in first and then assess how much the wellbore storage effect is? Would it be possible or practical even?
Yes, that is possible. We have done that in this well. You could do a surface shut-in first and then decide, okay, I need a downhole shut-in. But you only know the necessity of a downhole shut-in once you've done both and can compare them against each other. If you have a surface shut-in like this, well, in this case it's really extreme, but some surface shut-ins, they might look reasonably okay. For example, this black one. If you have this black one, first sight, it looks normal. It's not until you dive deeper into the topic that it looks like there are some wellbore storage effects. You don't really know until you've done it. So it might be best to test it once, a surface shut-in and a downhole shut-in, make a comparison for this specific well or this specific geological play, and then you can draw conclusions whether it's necessity for all future wells. And sometimes, or maybe quite often, you don't realize that what you're looking at are wellbore storage effects instead of reservoir effects.
Okay, there's another question here that as the person pointed out, geothermal wells are often large diameter with no production tubing. So is it common to find downhole shut-in tools that are appropriate for, say, a 9 and 5-inch casing?
I think so, but you should really check with the service companies because that's not my out of my knowledge. I know that you have to install them, but how to install them, that's not my cup of tea. Check with your service supplier.
Is the well testing program using downhole shut-in different for, say, if you expect more than one feed zone in your well, or is it just the same?
Sorry, could you repeat that question, please?
Sorry. Would you recommend, is there any change in the downhole in the well testing program using downhole shut-in if you expect that your well has more than one feed zone?
Yeah, that's a good one. If you have more than one feed zone, then it will always be difficult to distinguish between the feed zones based on your well test alone. I'm not sure if it's possible, but maybe you want to try to test the two zones individually by shutting off a certain zone, test that one, and then the other way around. So you test them individually or separately, because combining two different feed zones in one well test, yeah, then you measure a skin or a reservoir property, but you don't know where it's coming from. So that will be complicated anyway, irrespective of a down or shut-in or not. A PLT might help in analyzing different feed zones.
I mean, it's a bit tricky, right? Because on one hand, you want to collect as much data as you can, but also on the other hand, there are more practical considerations that, of course, you want to save on costs and you want to get to production as soon as you can. So, can you comment on how would you propose a good balance would be between those kinds of paradigms?
Yeah, it depends very much on the phase a certain project in. If it's the first well that you drill, you might need a well test in order to decide whether you're going to drill the second well at all or not. Yeah, it's hard to say because every well and reservoir and project is unique.
Yeah, I mean, I would think that doing such a detailed data collection campaign would be fairly useful in the, say, early stages of development when you want to reduce risks as much as possible and you
Yeah.
want to characterize the reservoir as much as possible. But say if you have a field where you already have 10 drilled wells, would you think that it's still practical to do such a procedure?
I think you should still do it, yeah, because for example, in this specific case, if you have a surface shut in, then you might think you have no skin. Well, you do have, in this case, quite a large skin. And a skin means, by definition, an additional pressure drop. And the pump, by definition, has to compensate for that. And the pump, by definition, costs a lot of OPEX. So a skin can be translated directly to OPEX. If you've done a surface shut-in and you think you have no skin, then you are wasting OPEX. Well, you could have removed the skin. And do not underestimate the costs of a skin. A skin of one, I calculated once, the skin of one adds up on a yearly basis to additional electricity consumption of 25,000 euros. And so if you have a skin while not realizing it, a skin of 10, that will cost you 250,000 euro OPEX on a yearly basis. So I would recommend a downhole shut-in, so you know whether you have a skin of 0 or not. In the case it appears that you have a skin of 10, we should spend a little bit of capex on an acidizing job, for example. That saves you quite a lot of money on a yearly basis. So even for wells that are on production already, I still recommend doing a test at least once, and then compare those results with the other wells in the vicinity, so you can investigate how severe the well storage effects are. And maybe you can also draw conclusions regarding the connectivity of the reservoir. Are two wells in communication with each other? If you think there is no fault and think that wells are connected, well, there is a fact of fault that might change your view on a further development of the field.
Okay, then, and on that note, I think that's an excellent way to finish the webinar. In that, of course, these are data collection exercises, and they do have cost implications. But on the other hand, they also have implications on such things as operational expenses in terms of pump
Yeah,
output and also pump sizing and pump design. So
yeah,
yeah, I mean it's a good balance. I think that the scientific data is also has implications on expenses.
yeah, that's right. Yeah.
Yeah. Okay. And on that note, I'd like to thank you, Peter, for that presentation. It was this is all very revolutionary, I think, and I hope that people start to think about such things. I mean, we can challenge existing practices, of course, and we have to be open to them.
Yeah, I hope so.
Okay, then. So thank you to everyone who attended the webinar. Watch out for another one in 2 weeks, and we'll have something else interesting for you. Thank you. Have a happy weekend.
Thank you. Goodbye.
Bye.